Okay, so this is a second application of Ampere's law. It's the third hour of Physics 1C for April 21st. So we're now talking about the magnetic field created by a toroid. This is a picture of a toroid. So it's often used to create an almost uniform magnetic field in some enclosed area. The device consists of a conducting wire wrapped around a ring or torus made of a non-conducting material. So the torus could be like cardboard, it could be a piece of plastic, it could be carbon, something like that. It has closely spaced turns of wire, and we want to calculate the magnetic field in the region occupied by the torus at a distance r away from the center. Okay. So the inner radius is b, the outer radius is c, and we're looking for the magnetic field right in the center. Okay. The way that the wire is wrapped is such that, I'll draw on here, but then I'll erase the direction of the current. We use red, I guess. It flows in this direction, right? So it flows through here, and then it goes into the page right there, and then it comes back around here, and it comes out of the page here. So that's x. But then it flows this way, this way, this way, this way. This is the direction the current's flowing, always toward the inside of the loop. And then on the inside, it goes, into the page here, it goes into the page here, it goes into the page here, and so on and so forth, until it wraps all the way around at the end and comes back out here, right? So that's the direction of your current. It goes in and then out, and then back in again. Okay? So we want to find the electric field, or the magnetic field, I should say, in the region here, right? And we're going to do that by drawing a loop, which is defined as loop 1 right here, straight through the inside of every one of these rings, right? And then we want to use Ampere's law. Integral b dot ds is going to be equal to mu naught multiplied by the current enclosed by our loop. And specifically, we're looking at loop 1 right now, where we know that at the center of any one of these loops of wire, based on the direction that the current is flowing here, right? If I consider, for example, a loop of wire that's oriented like this, it comes back around like this, where the current is flowing in this wire in a direction like that, and then back this way, so that this is the front. Oops, sorry. So that this is the front, and that's the back. Then the direction of the magnetic field created at the center of this object is going to point that way. That's the direction of the magnetic field. So it's always going to be tangent to the path. And up here at the top, you can see an arrow for the ds from the path and b, and that they point in exactly the same direction. So this would be a loop like this. The loop of wire up here would be a loop of wire like that one right there is a loop of wire that goes around like this. And the the current is flowing down this way and back up this way. And that's going to create a magnetic field at its center that points this way. That's like the loop right up here where that is drawn. Okay? So that means that the magnetic field and the ds vector point in the same direction, which means we can simplify the left-hand side of this equation. Looks like I'm stuck on red for now. I noticed a second ago that if I did something like this, and then I start drawing again, and I do this. Looks like it works. Okay. So the magnetic fields and the ds vector point in the same direction. So this is going to become b times the integral of ds. If you look at the loop that we've created here that goes around in a circle like this, it has a radius r, right? Which means the integral of ds is going to be 2 pi r, as it pretty much always is in these type of problems. The right-hand side, we just need to calculate the current that's enclosed by our loop. So all the places where I've drawn x's right here, there are little wires that are piercing through the inside area of our loop right here, right? Loop 1 creates a surface. The surface is basically the screen of the page right here. Whoops, I did not mean to do that. And basically every time that you go inside, you're going to get a contribution to your I enclosed, right? So the first thing pierces through, and then the second one, and the third one, and the fourth one, until you have exactly in turns of wire. So if it was two loops that went through our, sorry, if it was two pieces of wire that went through our loop, you would have 2i, but we have in this case n times I. All right. So we end up getting that the magnetic field in this case is going to be equal to mu naught times the number of turns times I divided by 2 pi times r. It's a pretty simple derivation for what would otherwise be kind of a complicated thing to use the BO sub r law for. Okay. Anybody have any questions? Really the solution here, like if you compare it to, so this is for a toroid. For a solenoid, we just found that it was mu naught, it was just n divided by L times I, right? You can maybe see the similarity because this is basically L, right? The quote, the length of your toroid is the circumference of the toroid, right? Or the inner portion of it. But this magnetic field would really just be at the center. Not the center, I don't know what you'd call that, the, you know, in the middle of the rings, basically. Okay, these are two different ways to produce magnetic fields. The solenoid produces a magnetic field that's like a bunch of straight lines, right? And the toroid produces a magnetic field that is circular in nature. That would be for the toroid, and then this would be for the solenoid over here. All right. You guys have any questions about that? If not, then I think we have one more problem that I want to cover today. All right, let me go back up to our list of things. I think we're talking about the flux through looped wire now, right? We're actually going to have a little more extra time, so we're going to use that to talk as an introduction to Faraday's law. So let's do this last problem here. There it is. Move it up some. Okay, we've done a lot of derivations today. This is not really a derivation so much as it's an actual problem. Oh, I see what happened. It's moved up so that the notes will be a little more, I'll have so much blank space. Okay. So this is our picture, and I'll draw a picture over to the side so it's clear what's going on. We have a rectangular loop of width A and length B. This rectangular loop, width A and length B, right? It's located near a long wire carrying a current I. So there's the current I right there. The distance between the wire and the closest side of the loop is C. The wire is parallel to the long side of the loop. We want to find the total magnetic flux through the loop due to the current in the wire. Okay? The total magnetic flux through this loop, and again, like I'll draw the picture. You take a wire, it carries current in this direction. It's a long wire, right? Near this wire, you put a loop. This is our loop. The loop has dimensions B on this side and A on this side. This loop does not have any current in it at all. It's just a loop. It's a box. And what we want to calculate is what is the magnetic flux through this object right here. And I'm going to remind you that magnetic flux is given by this expression. It's the surface integral of the magnetic field dot product with dA. Okay? It's just like electric flux, except you replace the E with a B. Now, this magnetic, this wire that carries current I, it's going to produce magnetic fields such that the magnetic field would be very strong when you're close to the wire, but it's going to start to get weaker as you get farther away from the wire. Okay? The X's are just going to get smaller as a representation that the field just gets weaker and weaker as you move farther and farther away from the wire. Okay? We know that this wire, the wire right there, produces a magnetic field that's equal to, because it's a long wire, mu naught times I over 2 pi r. All right, so our goal is to find the flux in this case. where the magnetic field is changing as you get farther and farther away from the wire. All right? And the way that we're going to do that is we're going to say, suppose that we break our loop up into tiny little strips that have thickness dr. Okay? So we break off from our loop a tiny strip, like here and here. We say that that strip that we've cut off has some thickness to it, and we're going to say that it's a distance r away right here. In fact, I should make that a different color so it stands out. We're going to say that this distance here, we're going to call r, and the thickness of the cut, as shown in the picture, is going to be dr. And we're going to use that to calculate the flux. So let's do that. So there's our equation, right? We need to take the integral of b dot dA, all right? So what is dA? dA is a vector that points normal to the surface enclosed by your loop, okay? So dA is a vector that points normal or perpendicular to your loop. And I'll say it's normal to the surface enclosed by the loop. In this case, I'm going to say that we're going to say that the dA vector is going to point into the page, okay? Because that's the direction the magnetic field points, okay? So our dA vector, right, is going to be like this, into the page. And it's actually here. This is it. This is the area. This is the dA. This thing right here is dA. And I'm saying that, like, this strip thing here is dA in that equation. And I'm saying that the vector dA points into the page in the same direction as the magnetic field. It points into the page. That is your dA right there. That thing is dA. The strip. It's the infinitesimal area of the loop. So what we can do now is say, through that one little loop, okay, through that one little area, there's going to be some magnetic flux, and it's going to be equal to b dot dA. Okay, we're not going to do the integral first because I think the integral can be very complicated. We're just going to say that through our little sliver, the flux is going to be the value of the magnetic field at that location, dot product with this dA. Now, this is going to be equal to, well, we know B, right? B is equal to mu naught I divided by 2 pi r. That's B. The dot product is going to tell us that this is actually just going to become BdA because B and A point in the same direction. Okay, so this is going to reduce down to just this. Well, what's dA? dA is going to be the area of this little piece right here. Maybe one of you guys can tell me, what is it equal to? What is the area of that sliver that has a length B and a thickness dr? It's like a rectangle, right? So what would the area of that thing be? This little thing. Yep, B times dr, exactly. It's just the length times the thickness, right? So BdA now has become B, mu naught I over 2 pi r, times B, little b, times dr. Right? That's your differential flux, right? Your infinitesimal flux through that piece. So to find the total flux, then, we just need to integrate that, right? The total flux is going to be the integral of mu naught I over 2 pi r dr. Well, and then there's a b too, but that's just a constant. We can pull that out. We're just integrating that, right? Really, that amounts to integrating this. Mu naught I b over 2 pi integral dr over r. And we need to integrate this from all the values of r for where our surface is. The lowest value of r would be this distance right here, which is called c. The highest value of r is going to be this distance. What is that? This is the left edge, right? What's the right edge? What's the r value going to be from here to here? That's c, right? What's this distance from here to here on the bottom? A minus c? Typo? A is this. C is this. So it's A plus C. And I would argue that the limits would be C to A plus C. Does that make sense? So, any questions about that? We got to integrate for the slips on the left all the way to the slips on the right. Yeah, I understand. It's hard to. Oh, on my picture, it does look like that it's A is just this side basically. I don't know if you can see from. That's why I put the picture in there too. That's A plus C. What is this integral gonna give you if we evaluate this integral right here? What are we gonna get? The integral of 1 over r dr log r, right? So it's gonna be the natural log this is gonna show up in a homework set that you're gonna have for next month. This type of problem, because this is kind of an introduction to the kind of calculations we're gonna be doing with Faraday's law. Okay, do you guys have any questions? That's the flux, right? That's what the flux is, yeah? That's what it is. That is the magnetic flux through that loop, right? This is equal to, let me drive this point home just a little bit here. This is equal to the magnetic flux. And if we pick some values, we could actually calculate what this would be, right? Let's pick some values. Let's say that the loop is exactly 1 centimeter away, okay? And let's say that the size of the loop is 2 centimeters on the bottom, so we make A equal to 2 cm. We also need a current. Let's use something simple. Let's use like, let's say 3 milliamps. All right, and let's calculate what the flux would be, right? So then the flux is going to be equal to mu naught, right? Mu naught is 4 pi times 10 to the negative 7 Tesla meter over amp. And then, I think that's the right equation, divided by 2 pi. And then times the current, which is 3 milliamps, so we'll have 0.003 amps. And then we've got the natural log part here. Is this Tesla meters squared? I gotta go to one of our equations here. So what is it? B equal to mu naught I over 2 pi r. So mu naught has dimensions of B times I divided by, oh no, not B times I. B times R, 2 pi. No, it's Tesla meter per amp, right? No, that's right, okay. And for this, we're multiplying by, oh, I left something out. That's the reason I was getting confused. The units weren't working out. In my final equation right here, there's supposed to be a B right here. Sorry, that equation is correct. I dropped the B somehow when I wrote it up there originally, but that B is there. So we also need to know what B is, right? So let's make B equal to 4 cm, the width. So we multiply by 0.04 for B. And then we just need to do the natural log of A plus C, which would be 2 plus 1, which is 3, divided by C, which is 1, right? So the natural log of 3, basically. And that would give us a value. Calculate this real quick. You can see it's not going to be a very big number, but... So I get, man, that seems really tiny. So I got 4.2 and it's times 10 to the negative 12. And then the unit here is going to be Tesla meters squared. A Tesla meter squared is also equal to a Weber bit. That's the answer. That's the flux. That's the flux through to one loop. And it's also a very tiny loop. If we made the loop larger, right, like we made this bigger, B, the size of the flux would scale with that too, right? We could also make the current a lot bigger if we want to. We could have 3 amps of current, and we'd have 10 to the negative 9. But anyway, oh my god, that's not the magnetic field. What's wrong with me? I made that mistake twice now, too. This isn't the field. It's this. It's flux. Sorry. The difference is key. This is flux. Flux. Magnetic flux. Alright, let me stop for a second and see if you guys have any questions. What we've done now is we found the magnetic flux through a loop of wire. And we did a calculation to see what it was, but this was our answer. You're definitely going to see this show up. Ooh, what's going on with this program? It's not letting me select. I have to go here, right? You're definitely going to see this equation here show up in your homework on a couple problems. Finding the flux through a loop. So do you guys have any questions about it? Okay, if not, then I think that means we can start talking about the next chapter. And talk about why we care about this quantity. Like, why should you care about magnetic flux? Why is it important? Why does it matter? This directly leads us into something that's called Faraday's Law. All right, as an introduction to this, just to give you some background on what we've done in this class. A point charge that's stationary, okay, a stationary point charge, this thing produces an electric field, right? And the field lines, well, they look, you know, like this. It produces an electric field. But then we found that if you take that same object and you take a whole bunch of them, right, and you make them all move in a wire with some current I, we find that basically in this scenario, moving point charges, just moving charges in general, what do these things produce? What have we been learning over the last few weeks? What do these produce? Moving point charges. Yeah, these produce magnetic fields. And what do they look like? Well, they kind of like wrap around the object like this, given by the right-hand rule. You've got these circular magnetic fields that are produced here, right? So stationary point charges produce an electric field. Moving point charges produce a magnetic field, right? So what happens then if you take a magnetic field, like a magnet, and you move it near a wire that doesn't have current in it? Okay? That's the opposite of this, right? Suppose that I already have a magnetic field. We now know how to produce them, okay? But suppose that I give you a magnet, okay? Right? And I'm going to connect this with something else we learned about today. Suppose I take a solenoid that has no current in it, okay? So I take my magnet, right? And I get myself an air core solenoid, but I don't actually put, any current through it, right? So all I do is I take a wire and I wrap it around here. Okay, we wrap it several times. I'm not going to do too many of these. I don't want to like sit here drawing loops the whole time. But whoops, last line I didn't need to do. We take our wire and we do the following. We connect it up to a meter, a voltmeter in particular. So we connect this up to something that reads out, God, I wish we could do labs, voltmeter. So this thing reads out voltage, right? And let's say that when it's in the middle, it reads 0, and over here it reads positive voltage, and over here it reads negative voltage. Make that a little clearer by doing those in different. So over here, this is going to be positive voltage over here. Maybe it goes up to plus 3 volts on this side, and maybe it goes down to 3 volts on this side. I just mean the meter, right? So maybe there's like 3 lines, right? And this is -1, -2, and this is -3, right? And this is +1, +2, and this is +3. And then you've got a needle in here, right? And the needle is basically going to swing back and forth. So there's my needle. Currently it reads 0 because there's just a magnet and the magnet's sitting still, right? So if moving point charges produce a magnetic field, maybe if we move the magnet, okay, maybe if we take this magnet and we push it into the solenoid, right? Maybe the motion of the magnet, and remember that the magnet, okay, the magnet has a magnetic field, right? You can say in a very simple sense that the magnitude of the magnetic field kind of just points, the direction of the magnetic field kind of just points like that, okay? The magnet has a magnetic field, and we're going to push that magnetic field into the solenoid, all right? And what happens is that when you do this, you get a readout in the voltage. If you push it in, the thing's going to swing maybe to the right. If you pull it out, the thing's going to swing to the left. It turns out that if you take a magnet and you push it into a coil of wire, you're going to get voltage. What does voltage mean? That means that you actually have moving point charges, right? I.e., the motion of the magnet into here, and now I'm going to have to do a rule that I haven't taught you guys yet to figure out what direction it's going to go, is going to make it so that the current is going to, when the magnet moves in, the current in this case is going to flow like this, right? Yep. Okay. And I'm going to say that that's the direction of the current. What I'm going to do is I'm going to say that that kind of current right there is going to be called induced current. And I'm going to say in more details actually that when the magnet is pushed into the loop, I'll say into the solenoid, into the loop, it's just the coil. Oops. A current begins to flow. And we often say a current is induced. That's the language we're going to use, is induced. So you could call it like I with a little I and D here, and say that that is representing the induced current. The word induced comes from induction. Kind of like deduction, but induction. And it represents the idea that the motion of this magnet near the loop of wire causes voltage in the wire. Okay? And if the current was flowing as I have it here, then what direction would that voltage be? Well, it would be, it's going to flow, let's see, up around here. Right, so it's going this way, back this way. So it would have to come from here, which means it's coming this way, which means it's going this way. Yeah, up this way, this way, this way, this way. Yeah, that looks right, right? In which case, this thing is actually going to read out positive voltage. It's going to swing over to here. You know, the needle is going to swing all the way to here. Positive voltage. And then when you... What's up? Correct. Yeah, the direction of the current that I'm giving you here is if the north end of the magnet's pushed into the solenoid. If we flip it around and push the south end, the voltage will read the opposite way. And if you push it in, it reads one way, and when you pull it out, it's going to read the other way. Does that make sense? Yeah. I really wish I could show this demo to you. This is one of the most interesting things in all of physics to me. The fact that moving point charges create a magnetic field, and that moving magnets create or cause charges to move as well. You know, so that means that, well, that's it. We basically, this is all of electricity and magnetism. Faraday's law is the last piece of it. Point charges produce electric fields. Moving point charges produce magnetic fields. And moving magnets produce electric currents, which is just moving point charges, right? Stationary point charges, electric fields. Currents produce magnetic fields. Moving magnets produce currents. That's it. That's electromagnetism. That's the summary of everything about electromagnetism. And each one of those statements is encased in one of Maxwell's equations, right? Maxwell's equations are Gauss's laws, Faraday's law, and Ampere's law. And specifically how Faraday's law works is by this equation right here. We say that there's an induced current, okay? But we also talk about an induced EMF. So the symbol I use for that is EMF with a little I and D. This is going to represent the induced EMF, right? If there's an induced current, there's also, that's generated by an induced EMF. And what Faraday's law states is the EMF that's induced, in our loop is equal to the time rate of change of the magnetic flux through the coil. There's a negative sign, and the number of turns in your coil also affects this. So I'll put in front of here an N. And we'll move here. Let's just try that again. Put a negative and then an N right here. This is Faraday's law. What we call Faraday's law. I don't know he would have ever used this word, this phrase. Mostly what Faraday did was he built stuff like this, and he realized that if he just takes the magnet and he sticks it inside of here, if the magnet doesn't move, you get no voltage. You only get voltage when the magnet moves, okay? And there's a couple other ways you can do it, but in general, this is the statement of what Faraday's law is, that the EMF induced is equal to the time rate of change of the magnetic flux. That means that you get an induced EMF in your wire anytime the flux changes, okay? That's really important to understand. You get an induced EMF when the flux through the loop changes, okay? So I'm going to talk about ways in which that can happen, right? There's 3 ways in which that can happen. So keep in mind that our expression for flux is this. But in a very simple sense, this thing can be reduced down to just flux being kind of basically equal to BA cos theta, okay, where, you know, what does that mean? That means, well, suppose I have a magnetic field, and I take a loop, and I orient the loop like this. There's my loop. Then the things that matter are the area of the loop, right? That's the area A. The angle between the area vector and the magnetic field, right? This is the area vector. That's theta, right? And what else do you have? You have BA and you have theta. I've got them all on there, right? So the induced EMF happens when the flux through the loop changes. Can you guys tell me, what are the 3 ways that the flux through the loop can change? There's 3 ways. What are the 3 ways that the flux can change through this loop? Okay? We take a piece of wire, we put it in a magnetic field. How can I change the flux? What are the 3 ways that I can change the flux? Okay, that's number 1. Let's write that one down. So change the angle. How will we change the angle? Let's talk about that one first real quick. How will we change the angle? What can we do to change the angle with respect to, like in this case? But what would that mean? Rotate it, right? You'd rotate it, exactly. That's what a generator is. A generator is a device where you take a loop, you attach it so that it has an axis to rotate along, and you have a hand crank, and you just rotate it in a circle like this. The effect is that the loop rotates. This picture's horrible. Imagine you've got a handle, and you connect it along the axis of your loop right here, and you just spin it, right? You make it so the loop just spins and spins and spins and spins. That's going to generate an EMF in your loop, right? That's how we produce power in America, and the rest of the world as well. We have a little loop, we put it inside a magnetic field, right? Connect it to a hamster wheel, that's right. You could produce electricity by having a hamster run around a little thing that makes this thing move, right? You could also make it so that you take this piece and you connect it to a water wheel and you connect it to a river, and then you'll generate electricity, right? Or you could do what we normally do, which is you take a vessel that has a hole cut into it, you fill the vessel with water, and you put some fire down here. So you burn some fire down here, right? And all of a sudden you get steam. Steam starts escaping, right? And then you just take a little turbine, right, that can take this steam. The turbine rotates, and then all you need to do is connect this turbine to a loop. A loop of wire. That's it. That's that simple. You boil water. It makes the turbine spin. You have a wire, and you place the whole thing in a magnetic field. And then the motion of that rotation of that basically generates electricity. Right? It generates an induced EMF. What is an induced EMF? It's electricity, basically. It's current. It's electric current. That's what happens. Anytime you rotate a loop of wire inside of a magnetic field, it generates electricity, basically. That's how a generator works. Like, if all the power went down in the city right now and you went to Lowe's and you had to buy a generator, it would basically be doing a combination of this into this. You'd put gasoline into it. The gasoline would burn. The burning of the gasoline would cause something in the system to rotate. That thing is connected to a magnet, is connected to a coil of wire, which is inside of a magnetic field, and that's it. That's how it works. That's how you generate electricity. Does that make sense? That's what Faraday's law says. This tells you how to generate electricity. This tells you how to power the world, right? Just by changing the angle. And the amazing thing is that the type of EMF that you would get if you were to rotate this at a constant rate, and we're going to prove this later on in more details, this is what the EMF would end up looking like if we just rotate it. If it's a constant rotation, the EMF is going to be a sine wave. A perfect sine wave. Because sometimes the flux, and we're going to get into more details about this, about where that negative sign comes from and stuff, but sometimes the flux is going to be increasing, sometimes the flux is going to be decreasing, and as a result, you're going to get an EMF like this. This is what we call alternating current. Alternating current, AC. That's what comes out of the wall. When you plug your stuff into the wall, what's happening is somewhere far away, there's a little loop of wire that's spinning, and it's doing its little hamster dance for you, basically. It's doing its little hamster wheel thing, as he's saying. Like, this little wire does all the work that you need to run your computers and to run your TV and your microwave and your lights and all those things. They're all run by a little spinning wire somewhere off in the desert. That wire may be connected to a windmill. It could be connected to something where you're burning fossil fuels. It could be connected to a hydroelectric power dam where the gravitational energy of water is converted into electricity. It could be any of those things just by changing the angle. That's what Faraday discovered. Faraday's the person that figured this out and the rules about how it works. Okay, does that all make sense? Do you guys find that fascinating? Or are you just really bored now because we've been in class for 2 hours? I would understand that. I find this to be utterly fascinating. So, all right. How else? 3 ways to change the flux. We only labeled 1, right? What else can we do? What's the second way that we can change the flux? How else could we change the flux? There's 3 factors, right? We just said angle. If the angle changes, that changes the flux, right? We've got these other 2 too, right? If B changes, right, you can change the magnetic field. Meaning the magnetic field could be growing or weakening or something like that. The magnetic field could just be produced by alternating current, which naturally does this, right? Let me give you an example of that. We said that if we take a solenoid, right? So we got our solenoid, right? All these loops of wire. Solenoid is just a bunch of loops of wire, right? And then we just have to have a little core here for that, right? Oh man, it's doing that thing again. So how did I do this? We click on this, we do something like that, and then I put the pin back down, and then it should work. Yep. So now we have a core for our solenoid, right? And then inside of there we said, okay, now there's going to be a magnetic field that's produced here, right? There's B. But what if the current flowing through this wire, okay, what if the current flowing through here is flowing in this way and then it's flowing out that way? But what if it's connected to a device, right, that produces this type of current, what we call AC current? What if it's connected to what's called an alternating current source? Well, then what's going to happen is the current as a function of time is going to look just like this. You know, we could also say the current here, it might be like reduced by the resistance, but the current is also going to look kind of like this. It's going to be changing over time. So if you change the magnetic field, right, then you also, you know, if you change the magnetic field, you can also produce an EMF. And this magnetic field would point to the right, and then the left, and then the right, and then the left, right? So what you could do is you could take another solenoid. This is where this picture is going to get really ugly, okay? I apologize for that. If I take another solenoid, right, and I wrap it around here, I'm only going to draw a couple loops for this one, okay? So let's say that I wrap another solenoid around here. I have a solenoid on top of a solenoid, one that's bigger than the other one, right? And then to these I attach a voltmeter. Put my little voltmeter in here. What's going to be happening now is that the angle isn't going to change between the loop, right? This is our external loop. The angle's not going to change, but the field is going to go back and forth, right? The field's going to be pointing this way, and then that way, and then this way, and then that way, and then this way, and then that way. Because the source is going to direct the current. The current sometimes goes this way, and sometimes it goes that way. And as a result, the field inside is going to flip back and forth, right? And what that's going to do is it's going to induce a voltage here that's going to swing back and forth and back and forth. And I wish I could show you this. I have so many demos for this stuff in the lab. But it actually happens that if you just take a loop of wire, you put an AC source on it so that the current changes, the field that's produced at the center changes, and then I can wrap something else around it, and it can consistently deliver power to this external coil that we put over it, right? This is what happens with wireless charging. Do any of you guys have wireless charging on your phones? This is how it works. It's how, if any of you have an electric toothbrush, this is how it works. It works through this principle of Faraday's Law, and the whole process is called induction. So that's an example of how you can change the magnetic field, okay? The other example of how you can change the magnetic field I showed you up here, you can just simply move the magnet inside of here. That changes spatially where the magnetic field is over time, and as a result, it changes the flux as well. Okay, do you guys have any questions? The third possibility is you can change the area of the loop. So, for example, you could make your loop change in size by getting smaller or bigger. That would also affect this. But I think the first two are the primary ways that you're going to find that you get this to work. And this is all called Faraday's Law of Induction. So this process we call induction. You ever see that word induction in reference to electricity? It's referring to this process. The fact that you can produce an EMF or a current by doing any of these things right here. You either change the angle of the loop relative to the field, you change the size of the field, or you change the area of the loop, or you do some combination of all of these. You can do them all if you want to, and all of them will have an effect on changing the flux, which will then, as long as this changes, as long as the flux changes, you get an EMF. It's not the change in the field that does it, it's the change in the flux. This program's getting really unresponsive. I wonder if it's because the document's getting so big. Got a lot of stuff today. All right. So that is an introduction to induction, which is one of the most fascinating things in physics, I think. Do you guys have any questions? Stop for a second. Have you guys ever heard of inductive heating? Like induction stoves? So there's electric stoves, but there's also what's called induction heating. And this might be too complicated to just throw at you guys, but the idea is that you take an iron or something pot and you place it on top of this type of stove, and the stove has electrical currents that are intentionally designed to produce currents inside of the metal, and it can be used for a certain type of... It's not the electrical stoves, but it's like... They look like the... You know what they look like? They're usually like just a flat plastic surface. Not always, but there's like this kind of... Yeah, anyway, I'm kind of going into details about something that I can't... Can I Google an image? You're not going to see much of it, but I'll pull it up, yeah. What is this? Inductive heating. Or induction stove? Is that what I want to search for? It's going to look like your normal stove. These pictures aren't exactly. What does this one look like? I mean, this picture kind of shows what it does. I'll pull this over here. So, yeah, let's just pull this up into a new tab. So, ceramic cooktop. There's an electromagnet down here. Okay. An electromagnet just means that you've got coils of wire wrapped around some type of a... And the idea is that this electromagnet produces magnetic fields. These lines are field lines. And the effect is that if the electromagnet is oscillating in terms of its field, it will cause currents inside of the, say it's conductive cookware. So like, this doesn't work with, you know, you have like ceramic cookware, for example. It doesn't work with that. Like the kind of white pots. It heats the pot up because it induces currents in the system, and those currents create friction, and resistance turns it into heat, basically. It heats up the pot. But see, you see how it's not like direct heating, though? Like, I've never, ever used one of these before. I've never even been in someone's house that has them. But I'm reasonably certain that if you took the pot off the stove, you could put your hand on the stove, and it probably wouldn't be hot. Does that make sense? Because the heating occurs only inside of conductive substances, and your hand's not conductive. Does that make any sense? They have one of those? Is it true? I don't want you to test this. If I'm wrong, don't test this, because I'm sure it does heat up due to the friction here. Is it true? It's really not hot. Is that right, Desminster? It's not hot at all? It's like actually cold, right? Apparently everyone's grandmother has one of these. That's cool that you guys actually know someone that has one. I've never seen one of these before. I've just heard of them. I think induction's amazing. But this is, if you think about it, similar to what happens with your phone chargers, right? Your phone charger works off the same principle, except that it's designed not to heat up. And the what's it called? I'm talking specifically about the, what are they called? The wireless, or, yeah. The ones you don't have to plug in. What is it called? Anyway. Yeah, you put the phone on top of a pad, right? And there's no direct connections. It works off the same process. Induction. Okay. You didn't test it, but your grandmother said so. She's probably right. Yep. Probably correct. Alright, that's Faraday's Law of Induction. It is utterly fascinating. It drives the energy of our world. It summarizes everything about electricity and magnetism and how they're all created. Yeah, but we've got all of Maxwell's laws now. You know, Maxwell's equations, you might say, right? Just label out what they are, because we can actually write them all out now, which is kind of cool. Here, let me go down just a little bit. We're going to go into a lot more detail about Faraday's Law of Induction. This is just an introduction to how it works, but you need to kind of realize the principal idea, which is that it's this change in magnetic flux. That's what we're going to be talking about for a few weeks here. Let's actually just write out what Maxwell's equations are now. We're gonna develop these in kind of more detail later, but here's what they are. We can write them down very quickly here. You might actually be able to recite them now. I don't know. 2 of them were introduced today. We did both of them today, actually. So they are Gauss's law, that's one. Number 2 is Gauss's law for magnetism, which states that if I do the same thing, if I do integral b dot dA, if I really want to be super, I should really say it's a surface integral, and I should have 2 little lines here. This is equal to 0, because there's no such thing as magnetic charge. This is Gauss's law for magnetism. These 2 equations describe what are called electro- and magnetostatics. Basically static phenomena, situations in which objects are at rest. The other 2 equations describe what happens when objects move. The first one is what's called Ampere's law that we learned today. The integral of b dot ds is equal to mu naught times I enclosed. Look at the similarity when you put them side by side like this. And then the other one is that is Faraday's law. And Faraday's law says that the EMF, okay, that's induced in a loop is equal to negative n. Again, we're going to talk about where that negative sign comes from tomorrow. dB dt. Now, these 2 may not look very similar to each other, but we can actually write them in a way that they will start to seem similar to each other. If you remember going back to what EMF is, EMF is basically equal to this. It's equal to the negative of the integral of E dot ds. Alright, so if we take that and we put it in here, all of a sudden these 2 equations start to look really similar. I'm sorry, this is a... That's not what I want to do. I'll put a little circle on there. If we replace the left-hand side now with integral E dot ds. Sorry, there's no negative sign here, is there? My bad. I don't think there's a negative sign here. We get that equation. Integral E dot ds is equal to negative n d phi dt. Now, these equations don't look perfectly symmetric, but the left-hand side is the same for all of them, right? Where's my Discord link? There we go. The left-hand side on the top is a surface integral, and on the bottom is a line integral. And I should also say specifically that these equations here describe... Oh no, what's going on? Sorry. These equations describe what we call electromagnetism, which is the study of what happens when things move, basically dynamics. So electrostatics and magnetostatics, and then electromagnetism is described by these. But yeah, left-hand side's the same. You'll notice the right-hand side is not quite the same, right? We don't have much time left, but anyone have any idea why? Why these two equations might look a little different from each other? They both involve doing a line integral, right? It's the line integral of b dot ds, and we say that's equal to mu naught I enclosed. And over here, we say the integral of E dot ds is equal to the rate of change of magnetic flux. Why do these two look so different? Anyone have any ideas? Specifically this. My god, this program is so laggy. I must just have too many things open. I wonder if I'm exceeding my RAM or something like that. No? This program just sucks? I need to, oh, I probably need to be, because I'm, oh, there we go. Any ideas? Why the left-hand side is the same on both of these? What on earth is this thing doing? I just want the selection tool. Anyway, what do you guys think? The left-hand side is the same for this one and this one. What about the right-hand side? Why would they be different? All right, here's a hint. These two are also different, right? When you do the flux, it's equal to the charge enclosed, right? But when you do the magnetic flux, you always get 0. Why is that? What's the reason why this one's always 0? Do you guys remember? That's part of it. What's the other reason? What is this? What does that mean? Q enclosed. What is Q? What kind of charge? What kind of charge is it? What is that? What kind of charge? Is it like mass charge? Is it spin charge? It's electric charge, right? Is there anything such thing as magnetic charge? There's no magnetic charges, right? Magnets always come in dipoles, right? You're always getting a dipole for a magnet. No matter how small you cut things down, even a single spinning electron has a very small magnetic field. Magnets always come in these like loops. These magnetic field lines always come in loops, which means there's no such thing as magnetic charge, right? Okay, what's this? What's the I enclosed in Ampere's law? What does I stand for? What kind of current? Yeah. So, okay, so why is there no plus mu naught I, but we don't call it I, we call it like I magnetic or something? Why is there no term like this? Why is that one not there? What's the reason? Why is there no magnetic current? The question makes sense? Why is there no magnetic current? They come in pairs. Exactly. You can't have magnetic current because it always comes in pairs. So any individual one of these has a total magnetic charge of 0, right? The total charge, if you could call it such a thing, the total charge of an individual dipole would be 0. So you can't have a flow. You can't have a flow of magnets. It won't do anything. It would just be, you couldn't call it magnetic current, right? That's why it doesn't show up over here, right? That's the reason why. There's no such thing as yeah. So here's the last piece of this. This equation's incomplete. There's another term. Okay, and I'm going to tell you what it is right now, and we're going to derive it later. Okay, this is the other term. We're going to have to prove to you where this comes from. But that's the full version. We need to get the green part in there. That's the last thing we'll do. Okay, but then there's like virtual complete symmetry between all the equations, and it shows the way that electricity and magnetism interact with each other, how it's the flow of electricity that produces magnetism, and it's the change of magnetism that produces electricity. You get that nice interaction between the two of them. That when one of them changes, you get the other one. When you have an electric field that's changing, it produces a magnetic field. When you have a magnetic field that's changing, it produces an electric field. And the cycle basically is just like repetitive. Once you have a changing magnetic field, it produces an electric field. If that electric field changes, it'll produce a magnetic field. If that magnetic field changes, it'll produce an electric field. And it'll just basically just oscillate between the two somehow. This phenomenon that I'm describing right now is basically the way that light works. And we'll develop that more as we go throughout the class. So there you go. There's Maxwell's. It's not one equation. No. It's Maxwell's equations. There's 4 of them. These things taken together with the force law, right? Which is that if you take Q and you do E plus VB, all of these things together describe all of electromagnetism. Everything you need to know. Those are effectively the conservation laws / like Newton's second law for 1C. That's it. We're halfway through the semester and we have all of the equations you need to do everything you want to do. Okay, that's a great place to stop. I'll wrap things up for now, and I'll stick around if you guys have any questions.